Java 8 to 17 to see the progress of how Java has delivered more security to the core platform. I'm usually giving talks that are like about security controls and how do you do this correct. This is something you could read on a blog. So I just want to be clear before you decide to stay, this is a pretty light talk, just reviewing again, history. Yeah, we're reviewing the history of Java security to see how we get to today. This is about the end of 2021. Java 18 just came out. Haven't even gotten the security analysis done. It's so fresh, just like a couple weeks ago, or like a week ago. So we'll get up to version 17. The major changes in Java happened around Java 8, 9, 10, and the many versions that we see in the last couple of years, they're releasing Java a lot more frequently with smaller enhancements. So this should be a nice, we're just gonna go over some crypto basically. This should be a nice light talk. My name is Jim. I'm honored to be a Java champion. Oracle has a Java champion program. It's a cult. It's a total like weird cult, let's be clear. And you cannot ask to be in it. Someone from the cult, the Java champion group, has to reach out and invite you in. Then you gotta like do weird cult stuff to demonstrate that you are of value to the Java champion community. This is the weirdest group I have ever been a part of. And I am in it, so I am part of the weird now as well. So like if I'm ever having a bad day or I just feel like entertaining myself, I just say something to the Java champion group and everyone argues about it for 3 days. It's so much fun. But anyways, let's just move on. Let's just move on. All right. Now, I want to start by saying that Java does have a big open community as part of the commercial activity that we see from Oracle. I've been a Java programmer for, wow, about 23 years. I started with Java 1.0.2 back at the very beginning of the language and have been working with Java my whole life. And I watched Sun manage the Java programming language for many years. I worked for Scott McNeely personally as to do executive dashboards for Scott and the executive team. So I was at the heart of Sun, working with Java for the executives of Sun. And it's honor to be there. And Sun did a real shit job managing Java, really bad. They did bad with security. They rolled it out. They did a lot of poor rollouts. They took care of their engineers. They were great people. They were very humanistic, caring people that cared about their engineers. They didn't do a good job managing this project. And then Oracle bought Sun. Now, I gotta be honest with you, the Oracle executives are the opposite. These are business people who want to make money and are a little less concerned about the people that work for them, in my opinion. But you know what? Their management of the Java programming language is outstanding. It really is. So it's kind of weird. It just come to mind now, but I wish Sun took better care of Java. And I was heartbroken when Oracle bought Sun. We all were, because Oracle has a bad reputation in the industry about everything they do. Sorry, they just kind of do. And it is to my amazement how much they've taken Java seriously, how much they've resourced the language, how much they've cared about security and supported the community. Not everyone in the Java community will agree with me, but that's my perspective as we watch Oracle fully take over the language. The licensing fees are a bit more expensive these days. Talk to Oracle. So the point I'm trying to make, though, is there's an open community around the Java programming language, and that's the JDK enhancement proposal process, the JEP process. And so a JEP is how you propose a change to the Java core ecosystem, and anyone can submit a proposal to enhance the Java language to affect change. And this takes a lot of work. They're looking for very detailed academic proposals that explain how you want to enhance the language. And if you put the work in, you're going to be listened to. The best example of this are these fine gentlemen, Mike Ernst and Werner Dietl. So they built type annotations. Who here is a Java programmer who understands the Java language? So great. So annotations are a real critical part of the language from like Java 7 and beyond, I believe. And this is one of the largest changes to the language at that time. And these are just two academics who wrote it themselves and then decided to build a JET proposal. It got accepted. It's now a core part of the language for the history of Java. So I think unlike other language ecosystems, if you want to do the work and you want to build a proper proposal, the Java community will accept your enhancement proposals to change the core language. I don't see that dynamic in many other languages, right? We see a lot of like small groups or dictators who run a language. This is an open process. A couple notes on crypto. When we look at all the changes in Java, it's mostly crypto-based, the kind of security enhancements we're going to review. And a quick note is, I would never use low-level Java crypto. Please don't use Java crypto functions. I think you should be using Google Google Tink is what I would use. Google Tink is a Java library that makes it really hard to get crypto wrong. It also integrates with key management systems. And so I hate to recommend a Google library, but in the Java ecosystem, there's dozens of crypto libraries that make the low-level crypto controls that we're going to go through easier to use. And every one of those libraries has major implementation flaws, except for Google Tink. This is built by a team of PhDs. It's well managed. It's used at Cash App. It's used at Google and many other places where they've done mammoth analysis of the work of Google Tink, and they found it to be robust. So I'm going to go over a lot of these, but this is what you should use underneath the hood of a library like Google Tink. We'll look at that a little bit later. The other thing is that they have a roadmap of their enhancements, and they change this URL on me like every couple of months for fun. Let me see if it's actually live here. I'm just curious. So there we go. The Java cryptographic roadmap. Yeah, accept all. There we go. Last updated 2019. They probably moved it somewhere else. So, yeah, they probably moved it and they just stopped maintaining this page. That's just the glory of Oracle. Let's just move on. So the largest change to Java security started happening in Java 8, where we begin our story. And again, this is the first time Java fully supported what's known as NSA Suite B cryptography for this era. These are a collection of encryption, symmetric, asymmetric, and digital signature algorithms that are best practice for U.S. systems. Forgive me, I'm an American. I have a U.S.-centric perspective. But NSA Suite B cryptography is a known pseudo-standard across the world of any applied cryptographer. We also see for the first time around Java 8 strong ephemeral cipher suites. We see better support for random numbers. The whole random number generation was rewritten, the new secure random class in this era. And all the weak algorithms are being deprecated by default. So there's one professional, Stuart Marks, in the Java ecosystem, and his nickname is Dr. Deprecator. His main job is to remove stuff from the language. And this is important because the more you get rid of the little thing, the more you solve the small problems and get those out of the way, the easier it's going to be to see and solve the big problems that we have in the language. So that's where we're going. I'm going to talk a lot about crypto, but again, Google, if you're a Java developer, I can't recommend it enough. Google Tink. It is by far the best practice in applied crypto. If you don't want to use a Google product because they invade the privacy of the world and monetize it, sorry, this is truth. Then you can also use another library that has a Java interface called libsodium. This is by Dan Bernstein, University of Chicago. It's a C-level library with Java hooks that, again, makes it easy for you as a developer to get crypto right. And in this era of privacy and enhanced security and the need to do application security correct, you're going to be tasked to do crypto solutions more and more throughout your career. So this is important stuff. So what else? So yes, please consider the third-party libraries of the world. There's Google Kezar and Google Tink. Like, they're sending teams of PhDs at these difficult library problems. And here's, again, libsodium from Dr. Dan Bernstein. these are the best ways to do crypto. Now that aside, let's go back to Java. Let's take a look at where are we going to start here? We're gonna hop up to Java 9, I guess. We're going to start the story, right? Java 8 is where we see the main crypto changes begin, and Java 9, now we're seeing major implementation of new crypto. Era in this, the story here is about 2018 now. We see DTLS. Why is DTLS important? Because I'm a video gamer. DTLS is the basic network protocol for asynchronous communication. Like if I'm a gamer and I'm sending events and I'm getting back events, basic internet protocol is not that great. So this is one of the main video gaming protocols. And we also see around this time something called the protocol negotiation extension. So I can have one main server with one set of certificates to host many, many different sites. I also see OCSP stapling around this era, end of 2018 or so, where now if I want to revoke a certificate, that protocol is available, the online certificate stapling protocol. We also see the beginning of SHA3 primitives. Now, SHA3 is not available yet in Java 9. SHA3 is really important for digital signatures, for cryptographic primitives, and for just the algorithm itself. So it took many, many versions of Java to roll out SHA3. This is the primitive first coming out in Java 9, and we're disabling older algorithms. So let's look at JEP 290 for a second. Around the same era, this is when deserialization was a really big problem in Java. In fact, let's go back a few years. If we look at 2016, this is where researcher Alvaro Munoz first declares that the entire Java ecosystem is vulnerable to a deserialization attack. What is a deserialization attack? You familiar with this? Think of real quick, an API endpoint. It's accepting binary data that it converts into a running object. This seems great, but it's not. It's the worst thing you could do. You should be using JSON for the most part as your data transport, not raw binary objects. But back in the day, when we're using... Where was I? Deserialization. So we really don't, and we have protocols like RMI, older protocols in the COM world in Microsoft, and the RMI world when it comes to Java. These are all raw binary object protocols. And the problem is I can take my raw binary, modify the class in some way, and when it deserializes into my code as the attacker on your server. So deserialization, even though we've been doing it for many years, around 2016, we realized this is a major problem. It can lead to RCE, remote code execution, where I send a malformed piece of data up to your server, it deserializes, and my operating system commands start running against your server. It doesn't get any worse than this. And early researchers talked about this since 2011, but we had no real examples of it. It was just a theory. And late 2016, we see that an actual collection gadget within the Java ecosystem is vulnerable, and now all of Java across the whole world is vulnerable. Just like the log4j problem we just had. We've had this problem in Java many times. That's the problem of these giant solve-every-problem languages. It's hard to lock them down. So one of the first big JEPs we see is JEP 290. Let's go take a look at this. Let me check my date. I think I'm getting my date a little, whoa, go back. I want to see the date on this. So this JEP 290 is one of the when did this first come out? Yeah, 2016, updated recently. So I'm a little out of date. It's released Java 9. We're now at the 2016 era. I'm going to catch up, I will. And JEP 290, filter incoming serialization data, shows up for the first time. I don't really like to use this because this means you're doing deserialization. But when it comes to security, it's easy to say, don't do this. Hey, developer, don't do this. I try to avoid that. Even better would be to say, hey, developer, what you're doing is really dangerous, and here's the best way we know how to lock it down today, to filter incoming deserialization data. This is the first major modern control that we see in the Java ecosystem in the last couple of years. And if we look at researchers around this time, Robert Secord was analyzing all the different attempts to fix this deserialization problem, and they were all incorrect except for this filter that was rolled into Java. So you have these custom filters now where I can specify what class is allowed to be deserialized. Again, this is when you're sending raw binary data to a Java server and it converts it to a running object. This is the filter you can use to limit that process. This is fundamental to Java security. I'm saying here that you may only deserialize the bicycle class. It may only be up to 78 bytes. The max array size is 10 and only one reference. And so now if the deserialization is anything other than that particular limit, it's going to fail. This will stop a wide class of attacks in this area. So what else do we have here? So there's a couple ways to implement it. I can implement this on a class-by-class basis. I can implement this on an entire system basis. And what we found out is that, and it's being used by other systems, by other subsystems in Java. What we found out, though, is there is no way to stop this problem. With the best breed defense I have today, I can stop certain attempts to crash my server. But if you allow me to set up a hash table and deserialize it, all I have to do is add a Java class, a Java binary, with a static block that instantiates the hash table, and I'll just add 2 entries with the same key. Can you have this 2 entries of the same key in a hash table? No, you may not. And as soon as you do that, the JVM is like, this is not possible to be in this state. And the JVM will crash. Because typically, if I'm programmatically adding elements to a hash table, the second time I add the key, it will overwrite or give me an exception. But if I'm now sending binary that says the hash table already has 2 keys, during deserialization, Java says, this is not a possible state, and the whole JVM seizes up. So yeah, just be aware that even though this is available, deserialization of raw binary data is an inherently dangerous process that you should never do. And there's so many attempts to make it work, and all of them that I know of are circumventable. What we want to do instead is use JSON. I wouldn't even use XML anymore. I've given up on XML years ago. XML is vulnerable to XML bomb attacks, XXE. There's several variants of XXE. There's external entity references, and there's the external entity expansion. So there's so many attacks against XML. Even though it's well locked down today, I see no reason to use it. Do you agree? Yes. Is anyone using XML for anything? What? Anders, what are you doing? Oh, you're a SAML guy. Yes. Oh, boo. Get out. Get out of my class, Anders. You and your SAML can leave. No, I'm kidding, Anders. Anders gave a talk on SAML 2, which uses XML. And what was the conclusion of your talk? Kill it. Burn it in fire. What should we use instead? JSON. Which protocol should we use instead of SAML 2? I forget. Okay, boom, exactly. So the era of XML is over. By the way, all the JSON parsers are vulnerable as well, especially in this era, 2017 now. Please, I would recommend you use the integrated language JSON parser of the Java language and keep away from third-party JSON libraries. They have a host of problems because how do JSON parsers work in the .NET and Java ecosystem? What do they fundamentally do? How does the different JSON parsers convert an object to a piece of JSON and then convert JSON back to an object? What's happening under the hood? Deserialization! Except for one library. Michael Samuel, Michael Samuel from Google wrote like a JSON parser that does all string manipulation, and we were not vulnerable to it. But for the most part, keep your JSON parsers up to date and keep away from esoteric third-party JSON parsers. Focus on what your language offers you. Let's bump up to, now let's look at JEP 273. JEP 273 is going to define the SHA3 extendable output function. Now, what do we care about that? Because this is the beginning of real random number generation in the world of Java, right? We have the new secure random class, which will allow you to do seeding, a pseudo-random number generator, reseeding. The problem with a pseudo-random number generator, you specify a seed, and then you start asking for random numbers. If I can discover that seed, I can pick up the entire sequence. That's why it's pseudo-random. And so I need to reseed periodically in order to have good random numbers at scale in Java. And we see the secure random class providing this capability for the first time. Let me move ahead. Let's look at JEP 287 now. Again, we're looking at we're getting closer to 2017, 2018, 2019 now, and this is the JEP that's implementing for the first time the SHA3 primitives. Why is SHA3 so important to cryptography? What do we use hashing algorithms for? What's that? No, sir. We would never use a hash algorithm for, I mean, with respect, we would never use SHA for a password. Why? Because if you take a password and hash it, take that hash and Google it, you'll get the password. What algorithm should we use for password storage? There's only 4 correct answers. Bcrypt, even though it truncates to 72 bytes. Damn you, Scott. But you're right. Bcrypt is a good algorithm, the minimal. What else? What's that? Argon, there's only one version of Argon is good. There's a lot of side channel attacks against it. There's Argon 2, there's Argon 2I, and there's Argon 2D. They're all flawed. So you want to use Argon 2ID is the good version of Argon for password storage. There's 2 algorithms. What else, Scott? PBKDF2, a US federal standard for FIPS, federal government compliance. You want to use it with an HMAC and not a low-level hash. What's the force algorithm that's good from Colin Percival? Scrypt. Those are, and none of these are hashing algorithms. They're either a key derivation function or a password hashing function. A SHA, this is a MIC, a message integrity code. And we never want to use that for password storage. I'm being pedantic with you, sir. So, oh, no, awesome. But why is SHA3 so important? What other algorithms depend on a good SHA3 implementation? I'm sorry? Digital signatures. What else? Asymmetric cryptography. And many other primitive algorithms will depend on us having a low-level hashing algorithm. So here we are in like Java 9, we're like 2017, 18, and this is where SHA3 first enters the Java ecosystem. We're going to come back to this in a little bit. No one's really using it, but this is where it's first, at least basically available. So now we're jumping up to Java 10. To class, it was about late 2018 or so now. And Nick is right. Any unencrypted traffic, it's not just a leak of data, it's an attack vector. If I'm on a network and I see someone using HTTP, I can inject my attack into their request stream so that their request launches the attack. Also, Bruce Schneier is right. Cryptography is only important if the rest of your system is secure. I've almost never seen an attacker actually go after the crypto. They'll go after key management, or they'll go after the application or access control or something else. Rarely do I need to break crypto directly to crack into a system. Scott, do you agree with that? Have you ever had to like brute force like a crypto key to get to succeed in a pen test? There's always an easier way. Now, TLS is the main protocol underneath HTTPS. right? And this is first, TLS 1.0 is now being rolled out in this era of Java 10. The spy can't view your data, they can't change the data, and you know you're visiting the right server because the initial public key in a TLS exchange is going to be signed by a certificate authority. Without that signature, as the attacker, I can inject my own public key in and take over. But the public key to start this TLS exchange, network security, going to be signed by an authority that specifies it's really for my server. So this is a critical part of network security, of transport security. We want to use TLS everywhere and always, and there's no excuse not to use HTTPS. So what we see in Java 10 for the first time is a mammoth update of root certificates to be in sync with most of the browsers of the day. This only happened until Java 10. Why does Java need certificates? Normally, it's your browser that's the client that needs to verify certificates. Why does Java need it? Because we often use Java as a client, like in a microservice. You make a request to my service, that service will load other data in an outbound way. And then Java's the client, and we got to have root certificates so we can verify the public key from the other server as we begin a TLS exchange. So JEP 319 is, let's check the date of this for fun. I'm gonna make sure I get my dates right. So now we're in, now we're up around, really? Yeah, it's a multi-layered, multi-releases. So I'm gonna back out of that. It's not helping my cause. JEP 319, somewhere along the JEP 319 path around Java 10, Oracle was kind enough to open source the root certificate list. So now for the first time, the Open JDK and Oracle JDK are in alignment when it comes to root certificates. I'm like, I didn't expect Oracle to do this. A lot of people, Sun wouldn't do it, but Oracle shows up and they start open sourcing big chunks of commercial Java. This is where I'm like, wow, Oracle, for all of their savage licensing, they're doing the right thing in the Java community. This takes us to Java 11. So how much time do I have? By the way, hey camera person, how are we doing on time? How much time left do I have? We're halfway through? Got it. So let's jump to Java 11 then. Excellent. So now we're getting a little more specific here, right? 3 major changes. We have a key, you know what a key agreement is? This is a key exchange algorithm. Why is this important? We got to understand how HTTPS works. HTTPS is a combination of 2 major things. A key exchange that's asymmetric and slow. And once we exchange a key, we drop to symmetric cryptography, which is blazingly fast, but it's only a 1-key system. And this key exchange algorithm, it's usually based on elliptical curve, Diffie-Hellman algorithm. And who created the curve constants in elliptical curve Diffie-Hellman originally? Anyone know where the United States NSA? Yeah, exactly. Some of the world's best cryptographers are in the NSA. So the NSA creates these hard-coded constant curves for key exchange. What's NSA's job, by the way? To build good crypto to protect your data? What's NSA's job? To spy. And you may not like the NSA. Guess which countries do spying in the world, sir? No, besides the US, what other countries have active spies in the world? All of them, right? So NSA probably wasn't giving us good curves. They probably had curves that were chosen on purpose so their supercomputers could crack key exchange and no one else could. So the European community is like, no, we're not going to use NSA curve constants because we know what's going on here. These are the new European curves around this era that are built by a community of mathematicians as opposed to spies in a spy agency whose job is to crack crypto. So anyways, this also, we're going to see this pop up later. The primitives for SHA-20 and Poly 1305 show up here as well. Again, European cryptographic standards at this point to counter AES for symmetric encryption and to counter RSA for asymmetric encryption. And also, we see the beginning of TLS 1.3 coming out. It was not that robust in Java 11, nor was the standard in this era, but it's out live. And here we go, JEP 3.14, new key agreement with non-RSA curves. There's a whole RFC for it, and it was built by an international community. I'm going to jump ahead here. So what else? Yes, now we have SHA-20, which is a new stream cipher that's faster than AES, only when there's no hardware acceleration. So in my mind, this is kind of a false promise, because guess which processors have hardware acceleration for AES built into it? That would be all of them, just about. So when does no hardware acceleration matter? When you're using IoT devices or non-standard. But for the most part, SHA-20 is always going to be slower than AES in Galois counter mode. The only time it's not is when it's usually an IoT-type device. But I see a lot of the European community who moved to SHA-20 praise its performance characteristics, which is just not true. In the real world, on any server or cloud service, AES Galois counter mode is always going to be better. But for those who don't want to use American standards, SHA-20 is still very reasonable. So I'm going to leave it at that. That's cool. There's no harm in using it. So at this era, TLS 1.2, and by the way, TLS 1.1, this is an older slide. TLS 1.1 is a dead algorithm. TLS 1.2 is well supported, but hard to configure correct. And TLS 1.3 is now live everywhere. Hey, Scott, let me ask you a question. Do you think we should, at the ASVS standard, deprecate TLS 1.2 at this point and only endorse 1.3? Or are you, Scott's one of the world's top experts in this technology, by the way. Do you think we should allow TLS 1.2 anymore? Oh. You know who's in my issue tracker at the ASVS standard right now? Christian Heinrich from Australia. And he's not the most gentle of participants, but he's real gifted, and he's pushing hard. He's like, why are you endorsing TLS 1.2? I'm like, because I'm realistic, Christian. He's like, yeah, but we're a standard. Let's get this right. He's almost convinced me. Come on, push me over the hood. Would you be okay if ASVS 5.0, which comes out later at the end of this year, if it said TLS 1.3 only and drop 1.2? Would you back that?
I couldn't with my clients. Like smart TV, smart devices, none of them do 1.3. So
I'm with you. We can use TLS 1.2 securely. All right, let me jump ahead here. So also, 2018 is when we were forced to start using TLS 1.1, and this is when PCI highly recommended we move to 1.2. Let's catch up now. So where are we next? Let's go to, I'm going to skip ahead a little bit. So now we see JEP 332 for the first time. This is the first time rolling out TLS 1.3, and we see AES with Galois counter mode now being available. This is an amazing innovation in the world of symmetric cryptography. This is an ultra high-speed variant stream cipher that is, for the most part, the recommended mode of AES we should be using today. There's a couple others that are better than GCM that were created in the last couple of years. They are not available in Java or in any widespread way. So today, if I had to make a choice for either cryptographic storage or cryptographic streaming, I'd use AES GCM, and we see this around Java 11 for the first time. What else do we have? Anything? Yeah, I'm just going to jump ahead here. What do we got? So now let's move to Java 12. Andy Warhol is right. You need to let you need to let the little things that would ordinarily bore you suddenly thrill you. I love this quote. This is the heart of Stuart Mark's work for Java 12. So there's no like direct security enhancements, but we see a huge number of little things being fixed that the cryptographic Java community wanted fixed for a long time. Like we're fixing problems with the security manager, the key tool to do key creation and similar is enhanced radically around this era. We're removing older algorithms. Cleaning up a lot of the mess was the job of Java 12. Now we're bumping up to Java 13. So and we're August of 2019 at this point. This is the beginning of the late modern Java era. Around this time, we see Java being released now every 6 months or so. And Oracle is going to keep up this pace. While Java 13 is a giant release, it's the beginning of Java 13, 14, 15, 16, 17, which are like 6-month release cycles. This is the biggest change in the Java ecosystem's release cycle. And we see support for native support for Microsoft integration into Java. Because if I'm running Java on a Microsoft server, I want access to all that .NET crypto goodness. It's complex to use, but instead of like building it myself in Java, if you're running Java JVM on a Microsoft system, you can just directly talk to the cryptographic API of your Microsoft operating system and get that directly in Java. This is a big deal. So we're beginning to remove some of the older certificate mechanisms here, where we have our first introduction of statelessness and JSON Web Tokens around 2019. We are enabling some more cipher suites. We have XML signature rolling up for the first time, and even more key tool enhancements for TLS. This is, again, Stuart Marks trying to get all the little things fixed to prepare for the Java 14 and above run. Now I'm going to finish this talk very early, so you can go play. Please bear with me. Now we're at March 2020. This is where Amazon root certificates get added. There's a whole bunch of minor deprecations of crypto, and the key tool is brought up to a modern key tool for the first time, in my opinion. The key tool is this little text command with very few advanced enhancements. In Java 14, we see like a little UI with it, a widespread increase in features, something that's now usable in the real world. Java 15 shows up October of 2020. This is where Edwards curve DSA signature shows up for the first time. Why is this important? Like, what's the main digital signature algorithm on the planet today? What's the main digital signature algorithm? To sign a JSON Web Token is one of its main uses. Or to sign a certificate in TLS. Absolutely. And is that a problem? Do you have any problem using RSA today? And as long as it's for a digital signature, RSA is awesome. We do not want to use it for authentication. We do want to use it for a signature, and it's great. Guess how many European architects want to use RSA as their digital signature, Scott? That'd be 0, exactly. Let's not use American crypto standards. So we have two digital signatures that are now embraced by the European community. And we see EC DSA, an older digital signature, and now for the first time in October 2020, we see Edwards curve DSA. This is an outrageously righteous algorithm that is significantly stronger than RSA. And this is, again, something I see the European community wanting to use more than RSA. SHA3 HMAC comes out. So the question was, what do we use hashing algorithm for? We use them as a primitive for a digital signature. We use them as a primitive for an HMAC. We use them as a primitive for key exchange algorithms. Hashing algorithms, I almost never use them by themselves. I'll use them as part of other algorithm families. And we have TLS 1.3 for the first time is usable in Java. Now we're up to a point where it's now production quality. It was really problematic up until Java 15, which is not too long ago. There's also the idea of code signing. We recommend that you do it for years, but now we see more developers actually wanting to use it for various reasons. So the whole Java, archive signing process is radically enhanced. And these newer algorithms, like Edwards curve DSA, is now available in the jar signing process. Now we're getting locked down. Java 16 is very recent, lasts like a couple years. It's March of 2021. Now we see SHA3 signatures available for the first time in Java a year ago. So this is like SHA3 RSA, SHA3 ECDSA, and SHA3 EDDSA, Edwards curve DSA. So now we have the most modern signatures with the most modern hashing algorithms available for the first time, and this should last us quite a few years based on the robustness of these primitives. Also, a whole bunch of old root certificates that had that had a weaker bit size were removed, and finally TLS 1.0 and 1.1 are now fully disabled out of the Java ecosystem. And there's no good reason that you should be re-enabling these old deprecated and broken algorithms. That takes us to the most recent version up until last week. Java 18 just came out, and I'm still reviewing it. So with Java 17, the big changes in Java 17 were in the foundation of Java itself. So we had a lot of problems in Java recently, right? The problems with log4j and similar. In fact, the way that Java 9 was set up was a major change in how the language was encapsulated. Java before Java 9 was one big monolithic programming language, and they began to break it up into separate pieces so you can deploy Java in a more modular way. This is a big mistake, in my opinion, and we saw how there's many attacks against that weakness. That, like, for example, we saw a problem in Spring recently, Spring for Shell. It's actually not that big of a problem, but that problem surfaced because of the modularization that happened in Java 9. So some choices to make Java more deployable really bit us in around 2019, 2020. So Java 17 rolled out last year. They go back to that Java modularization, and they build better encapsulation between these pieces to solve that problem. It took years to take a monolithic language, break it up into parts where it was done in a way that was actually secure and didn't weaken the language. And also, the whole deserialization API was completely revamped and enhanced, so it's a little bit more usable and more configurable as well. We also see that you can seal a Java class for the first time, which means you may not extend it in any way. And also, we see SHA-20 and Poly 1305, those critical European ciphers, rolled into the core of Java for the first time, the main Oracle provider. That brings us to today. We'll see Java 18 next time I see you. Since I spoke so much about, before I finish up, a few more notes. Let me rewind for a sec. I want to thank a few people. First of all, this is Sean Mullen. He is still the technical, that's actually not his picture, that's Brad Pitt. But Sean Mullen is a technical lead and architect of Oracle's Java ecosystem. I meet him at conferences every year, and I see the stress on this man's face. He's like holding up Java security. He's the main architect. This is no... What's up there? Oh, sorry. This is no easy job. And every time I see him, I can just see like the stress that supporting the security of this super complicated language puts on this man's shoulders. I'm a huge fan of Sean Mullen. He leads the OpenJDK security group. He hasn't quit yet. He's still doing it. And who is the main security architect of the .NET ecosystem? Do you know the .NETer who runs... I see him on Twitter a lot. We argue on a regular basis. Do you know the top .NET supporter at Microsoft, Scott? Anyone? I want to move on. But I know the individuals who manage Python security, .NET security, and Java security, and these individuals are really stressed out. It's too much of a job. So Sean should quit, go take an easy consulting job, make tons of money chilling out, but he's a believer. I just want to say I give him a lot of credit because it's an almost impossible job that he takes very seriously. So what can you do? If you care about Java, if you like to noodle into the internals of Java, what can you do? Well, if you see something that needs to be supported, create a JEP, Java Enhancement Proposal. And if you see proposals that you care about, support them, add comments, and so on. Maybe help them write code. Also, there's a whole quality outreach campaign that helps open source groups handle this feedback. So there's a variety of ways that you can engage the Java ecosystem, give them your feedback, and make Java better than it is today. I'm going to go back to one. I have a few minutes here. I'm going to go do one more thing before we really finish up. I just want to jump into, I want to show you a few diagrams. We're going to go low level and explain what a digital signature is, and then we'll finish out. Just for fun. I spent a lot of years using digital signatures, and until I really didn't fundamentally understand them until I looked under the hood and actually read the algorithm. So let's just look at what is a digital signature under the hood, because digital signatures are now the heart of all identity. Let me say this again. As we go and look at authentication systems, session management systems, and identity providers, the entire world of identity is all about digital signatures now. Anyone know why that is? Why is a digital signature something that was just basically only used in the world of like SAML, which is crap, sorry, or it was used in the HTTPS world? I didn't use a lot of digital signatures, and now I use them every day. What change do we see in modern development that mandates understanding of digital signatures almost every day in almost every app? What artifact uses digital signatures? I agree, but there's a certain JSON Web Tokens. We're moving away from session management in the world of microservices, and we've already moved to JSON Web Tokens, which are stateless artifacts. So how does this work? You log into my system that's stateless, and I create a token that represents that you're logged in for 8 hours as a normal user, and I digitally sign it and give you a copy of it. And why am I using a digital signature? Because if you modify 1 bit in the token, make yourself an admin, or if you modify 1 bit in the signature, when you give me that token back, it's not going to be valid, and I'm going to reject it. So because we need JSON Web Tokens for stateless systems, and because we protect those tokens' integrity with a digital signature, digital signatures are now the heart of the entire identity ecosystem, and they have been for several years. So let's finish up and understand what these algorithms actually are. Now, keep in mind, when you're doing a digital signature, you don't get confidentiality. I can still read the message and see it right there. All that digital signatures do, they're going to make sure that it provides integrity, which means if I modify the data, the server is going to know it. So I start with the message, and I hash that message using some hash primitive. I want to use SHA3, only available recently in Java, but I'll use some hash function, and I'll get down to X number of bits, in this case, 256 bits. Then I'm going to encrypt it with the RSA algorithm using a private key, and that leaves me with a 256-bit digital signature. I got that digital signature now, and I attach it to the message, and I give it to you. You're John, you're an admin, the token is going to be live for another 8 hours, and I attach a digital signature to it. And if you look at this token, you can read it. But the digital signature, when you give it back to me, will stop you from editing it in a way that I will not know. So now that once you give me this token, that's the raw plain text token plus a digital signature, how does the server verify it? The server takes that message and the digital signature, they take the raw message, hash it, and get to that 256-bit, whatever the bit size is of the hashing algorithm. And then we decrypt the signature with the public key. That gives me back to the hash value. If the hash of the message and the hash of the signature that I decrypt matches, then that signature matches the data. That's a digital signature. It's super elegant the way this works. And again, remember, I'm not using hashing algorithms by themselves. I'm using them as part of other algorithms. So RSA by itself needs an internal hashing algorithm. And as of very recently, we have RSA and ECDSA and EDDSA all available with the SHA3 primitive for this kind of functionality. This is going to serve us for the next many years. And that primitive is now available in the world's most popular language, which is Java. By the way, for the last many years, what's been the most popular language? It's been Python. Python, we use it a lot for scripting and infrastructure, and there's all these frameworks now to do web and API development in Python. And guess what? A lot of companies pulled back away from that. Why? Python's a great language, but the ecosystem of third-party libraries that we need to build APIs is not as mature in Python as is in Java. So we saw like a lot of companies going to Python and building APIs, and they hit a threshold in terms of how fast they can build this code. And Python got slow because a lot of the libraries we needed are just not mature. So a lot of companies went back to Java. I'm surprised, to be honest with you, but that's exactly what happened. And ZDNet told us like 2 weeks ago that Java has now taken over Python as the world's most popular language. So with 7 minutes to spare, that's my talk on Java security. That's it. If you have questions for me, I'm jim@manico.com. I'm so happy you're here at NDC Security. Guess what's coming up next? In the next hour or two? What's an hour from now? The most important part of the conference, what is that? The party. I'll see you at the party tonight. Go forth and write secure code. Thank you for being here, everybody.